Right. This is section 6.2, and we are looking at the graphs of the other four trig functions. So we already looked at the graph of sine and cosine, and in this section, we will start out looking at tangent and then cotangent, and then we will look at cosecant and secant. So again, using that unit circle would be really helpful. Memorizing it would be even more helpful. What we have here is some values initially around the unit circle, and then we get angles that are not on the unit circle, and we want to find tangent at each of those values. Now remember, tangent is equal to sine over cosine. So if I want to evaluate tangent at pi over 6, I can find sine of pi over 6 over cosine of pi over 6. And sine of pi over 6 is 1/2, and cosine of pi over 6 is root 3 over 2. I can multiply by 2 over 2 and reduce out my denominators, and then I have 1 over the square root of 3. But we need to rationalize that, so multiplying by root 3 over root 3, we get square root of 3 over 3. And so that is tangent at pi over 6. Similarly for pi over 4 and pi over 3. And then these other ones we would have to type into our calculator because they are not things on the unit circle we know. And then at pi over 2, we have sine of pi over 2 over cosine of pi over 2. And at pi over 2, sine is 1 and cosine is 0. And we can't divide by 0. So tangent at pi over 2 is undefined. What that means is that we have an asymptote there. So taking a look now at the graph of tangent, we have an asymptote at pi over 2. At pi over 4, it's equal to 1. At 0, it's equal to 0. And like the note right here says, tangent is an odd function. If I have negative or tangent of negative x, that's equal to negative tangent of x. That means it's symmetric about the origin. And so we have a reflection across the origin of these points here. And at negative pi over 2, we will also have an asymptote. So the graph of tangent almost looks like a cubic function. And we have this right here. So this is a graph of tangent, and much like sine and cosine, you will have 5, not exactly points, because the start and end will be asymptotes. So those aren't points, but asymptotes. And then you'll have 3 points in between. The halfway point is 0. The first point is at -1, and the third quarter point is at +1. So this is the graph of tangent, and normally tangent goes from negative pi over 2 to pi over 2. And rather actually than having x in the middle there, I'm going to rewrite that and write bx minus c. And just like we did with sine and cosine, I can add c and divide by b to all 3 sides to find my new start and end. So this is my normal start and end. And then if we have shifts on it, we can change those. All right, let's look at cotangent. So cotangent, remember, is cosine over sine. So cosine over sine, at 0, cosine is 1 and sine is 0. So 1 divided by 0 would be undefined. And then at pi over 4, it's 1, pi over 2, 0, 3 pi over 4, -1. And again, you can plug in the sine and cosine values at each of these angles. And then at pi, it's undefined again. So what that means is that at 0 and at pi, cotangent has vertical asymptotes. And then at pi over 2, it's equal to 0. At pi over 4, it's equal to 1. And 3 pi over 4 is equal to -1. So same shape graph, just like sine and cosine were the same shape, but it looks a little bit different. So if I zoom out here and you can see both of them, let's kind of compare and contrast. I know it's rather small here, a little too far. So tangent is from negative pi over 2 to positive pi over 2. Cotangent is from 0 to pi. Tangent starts low and goes high. Cotangent starts high and goes low. They both are 0 halfway between. And they both have a period of pi. And this one also is a period of pi. If they have a b value, then it would be pi over b. So cotangent is normally bx minus c between 0 and pi, and then you could solve for those the x value by adding c and dividing by b. Now you'll notice I just whited out the equal to sign on these inequalities, and I didn't write one here. They actually shouldn't have equal to inequalities because at pi over 2, negative pi over 2 and positive pi over 2, and at 0 and at pi, these functions have asymptotes, so they are undefined there. They are not equal to there. All right, let's take a look at some information about the tangent graph. So again, just like I wrote on the previous page, the period is pi over b. If it doesn't have any shifts or period changes, then the period is pi. So this is the graph of several tangent graphs, just repeating the same period. So at negative pi over 2 and positive pi over 2, we have vertical asymptotes, and then every pi, we are having more asymptotes. All right, and then for tangent, again, we're looking at this from negative pi over 2 to positive pi over 2, that bx minus c in between. And then for cotangent, same information. Period is pi over b, or if there's no shift, then it would just be pi. Starts at 0, ends at pi, vertical asymptotes at multiples of pi. And then setting it up between 0 and pi for that bx minus c. You can read through more of the information here. It's just giving you step-by-step instructions of the things I've already gone over and how to graph them. So let's do some examples here. The first example, we have 2 tangent 1/2 x, and we want to graph from negative pi to 3 pi. So what we're going to be looking at here is setting that 1/2 pi, or I'm sorry, 1/2 x in between 0 or negative pi over 2 and pi over 2. And then we're going to multiply by 2 to get our denominator to cancel, and we've got to do that everywhere. And that means all of our denominators went away. So one period of this is from negative pi to positive pi. That means I have asymptotes there at negative pi and positive pi. And I realize I haven't actually given myself enough space to graph all the way to 3 pi, so I might have to try and squeeze that in. And then halfway between those asymptotes, it's equal to 0. The amplitude is 2, so instead of being 1 right here, they will be equal to 2. And then tangent starts low and goes high. And so those are those first quarter points. And if this is pi, halfway between 0 and pi would be pi over 2. And so this is my graph of that tangent function. I was supposed to graph all the way to 3 pi, but I don't have quite enough room on the edge of my paper here. So it won't be the same width of graph here, but this will be 3 pi and 2 pi. And then from negative pi to pi is a distance of 2 pi. And so from pi to 3 pi is that same distance. So 3 pi would be my next asymptote. And then my quarter points here, my halfway point starts low, goes high. And there's the next period of tangent. Okay, next time better planning when I don't leave myself enough space on the page. All right, the next one we have 3 cotangent 2x. So that 2x is going to go between 0 and pi, and we're going to divide by 2, and we get 0, x, and pi over 2. So from 0 to pi over 2 is going to be one period of cotangent, and that means I have asymptotes at 0 and at pi over 2. And halfway between 0 and pi over 2 is pi over 4, and that's where I would have my 0 Cotangent starts high and goes low. The amplitude is 3. So at this first quarter point, halfway between 0 and pi over 4 would be pi over 8. And then halfway between pi over 4 and pi over 2 would be 3 pi over 8. 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. And so this is my graph of cotangent. All right. So we've done an example of tangent and cotangent. Here are the graphs of secant and cosecant. So cosecant is sine's reciprocal function. CSC is cosecant, and that's 1 over sine of x. And so what we will do is we will first graph the sine function to help us. And then everywhere where sine is equal to 0, 1 over sine would be undefined. So we will have a vertical asymptote wherever sine equals 0. Wherever sine equals 1, well, 1 over 1 would still be 1. So they share this point right here and right here at -1. And then it's a curve up from there and curve down. Secant is very similar. Secant is the reciprocal of cosine. And again, we'll use the cosine graph to help us graph it. And everywhere cosine is 0, secant has a vertical asymptote. And then wherever secant or wherever cosine is 1, secant is also 1 or -1. And then curved up from there. So this is one period of secant. All right, so let's get into graphing secant and cosecant. And when we first do this, it would be helpful for us to kind of think through a table of points. So I've already put the theta or the angle values there. So looking at angles around the unit circle, counting every 45 degrees or pi over 4, that would be 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Finding the sine value at each of those. And then what we're going to do for the cosecant is it would be the reciprocal of that. Well, 1 over 0 is going to be undefined. So wherever sine is 0, cosecant is undefined. That means I have an asymptote there. And then wherever sine is 1, well, 1 over 1 is also going to be 1. And 1 over -1 is also -1. Now, these are the harder ones, and we only have to do it once because these are all root 2 over 2. But if I have 1 over the square root of 2 over 2, that's 1 times 2 over root 2. Flipping the second one, changing it to multiplication. And then I can rationalize, and then that becomes 2 on the bottom and 2 root 2 on top. I can reduce my 2's, and then that simplifies to the square root of 2. So this will be the square root of 2, this will be the square root of 2, this will be negative root 2, and negative root 2. And now that we have all of that, we can go ahead and graph. So graphing one period from 0 to 2 pi, pi over 2, and 3 pi over 2, 1, and -1. The sine function I'm going to do in pencil. So remember, sine is at 0, 0, and 0, and then at max, and then it's min. And there's my sine function. Now, wherever sine is equal to 0, cosecant has a vertical asymptote. So sine is 0 here, so we have a vertical asymptote. Sine is 0 here, so we have a vertical asymptote. Sine is 0 here, so we have a vertical asymptote. And then wherever sine equals 1, cosecant shares that value. So you shouldn't have a point like hovering above it. They should share this point, and then cosecant curves up. And then they share this point at -1, and cosecant curves down. And that's how you would graph cosecant. Graphing secant is very similar. You could go through the same kind of process, but with cosine. Let's look at some examples of graphing some of these functions. So here we have -3 secant of x over 2. So I'm going to graph cosine first, and I'm going to use this x over 2, and it will be between 0 and 2 pi. And I will multiply by 2. And then that cancels out, and I have 0 x and 4 pi. And so cosine or secant will start from 0 and end at 4 pi. I'm going to use the graph of cosine first. And we have a -3 as our amplitude. So normally cosine would start up here at the positive amplitude, but it's going to be at the negative amplitude since we have a negative out front. And here is our graph of that cosine function. Now, wherever cosine equals 0, secant has a vertical asymptote. So cosine is 0 here and here. And that means that secant shares this point at 1 and then is curved up, shares this point at -1 and is curved down. All right, and that's the graph of secant. All right. These last two kind of squeezed in here, so let me try and zoom in a bit. It says graph 1 period of the function -2 tangent pi x plus pi minus 1. So we have a vertical shift of -1. So real quickly, I'm just going to put a little dotted line here through -1. And then I'm going to put pi x plus pi between 0 and, or rather for tangent -pi/2 and +pi/2. So subtracting pi, we end up with -3 pi over 2 pi x and -pi over 2. And then to get rid of this pi next to the x, I can either divide by pi or multiply by 1 over pi. And that'll be a little bit easier on the outsides here to see it simplify. So here my pi's cancel and cancel and cancel. And what I'm left with then is -3 over 2 and x and -1/2. So -3 over 2 and -1/2 is where my graph starts and ends, which means that tangent has vertical asymptotes at those places. Now, I've already counted by -pi/4 here. If I go from -1/2 to -3 over 2, and I'm going to need some in-between points, I decided to start counting by -pi/4s. So -1/4, -2/4, 3/4, 4/4, which reduces to 1, 5/4, 6/4, which reduces to 3/2. So at -3 over 2 and -1/2, we have vertical asymptotes. And halfway in between, tangent equals 0. And then tangent normally starts low and goes high, but we have a negative out front. And so we're actually going to be starting high and going low. And I'm actually going to be needing to move these points because I still have a vertical shift that I have to account for. So all of those points that I just plotted there in pink need to move down 1. So this point is at 2, moving down 1, at 0, moving down 1, and at -2, moving down 1 to -3. That blue is my graph of that tangent function with all of those shifts. So that was as complicated a tan function as we could get. We have a vertical shift, a phase shift, a period change, and an amplitude with a negative out front. So definitely one of the more complicated graphs we could see. One more example here, it's asking us to graph 1 period of 4 cosecant pi/3 x minus pi/2 with a vertical shift of 1. So 1, 2, 3, 4, 5, 1, 2, 3, 4. And you can see I already have my x-axis labeled. Let me show you how I got those values there. So we have pi/3x minus pi/2 and 2 pi and 0. I'm going to add pi/2. And so I have pi/2, pi/3x, and 2 pi plus pi/2 is 5 pi/2. And in order to get rid of this pi/3, I'm going to multiply by 3 over pi. And what happens then is my pi's cancel, my 3's cancel, and then here my pi's cancel and I have 3 over 2, and here my pi's cancel and I have 15 over 2. So my graph goes from 3 over 2 to 15 over 2. So I counted by 1/2. So 1/2, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, 7 halves, 8 halves, 9 halves, 10 halves, 11 halves, 12 halves, 13 halves, 14 halves, 15 halves. So 3 1/2s, 9 1/2s, 15 1/2s. And then halfway between 3 and 9 would be 6 over 2, which is 3. And then this would be 12 over 2, which is 6. So let me change, instead of 6 over 2, I'll write that as 3. All right, and then we do have a vertical shift of up 1, so I'm going to go ahead and just get my little light line there as my new x-axis. And then we can go ahead and plot our points. So cosecant is using sine. So sine would be starting at 0, ending at 0, and halfway 0. I guess I'm already taking care of my shift. Normally I do the shift at the very end. You know what? I'll be consistent. I'll do the shift at the very end, so I'll change those. So starts at 0, ends at 0, halfway is 0, and at the first quarter point is up at our maximum. And then at the third quarter point is down at our minimum. And there is my sine graph. But remember, that's not actually part of our answer. We're just using that for cosecant. So wherever sine was 0, cosecant has a vertical asymptote. And then cosecant would curve up from here, but remember, we are shifting this graph up 1. So all of these points are moving up 1. So up 1, up 1, up 1, up 1, and up 1. And then our cosecant graph will go up from those points and down from those points. And there is our cosecant graph with all of those very complicated shifts. And that brings us to the end of this section.